Hi, this is my presentation by me, Jamie Maddox, about the routing protocol OSPF and all of the different intricacies it brings to a network. A good start to this would be to explain what OSPF is in general. OSPF can be defined as a routing protocol, which is a protocol to help create routes between routers that lead to subnets. As well, routing protocols are also meant to help in the event that there is a failure of an interface or router, making sure to adjust how information travels so it still ends up in the right destination. In the world of routing protocols, there are actually two kinds for different cases. These are interior and exterior. To get more of a well-rounded view on OSPF, it's best to explain these different types of routing protocols. Both interior and exterior can be shortened into IGP and EGP, respectively. As mentioned before, both interior and exterior routing protocols can be abbreviated. These abbreviated names use a less common term, gateway. This term refers to routers, the term still being used in other contexts like setting up a default gateway. The main difference between the two types is that one allows for communication within one autonomous system, while the other connects each system to one another. These systems roughly encompass a public network, such as a library or business. Similar to public IPs, a business has to purchase rights to an AS number. In America, the nonprofit ARIN gives out these numbers as well as public IP addresses. Within the world of routing protocols, many have been made and can be used in some smaller settings, but for the most part, a majority of networks today either choose OSPF or EIGRP. This is because older routing protocol versions simply aren't reliable or don't scale very well. For example, one of the first routing protocols to come out, RIP, chooses the best path by hop count. This means that if one path has higher bandwidth while the other has a low bandwidth but only one hop, RIP will prioritize the slower path. Both OSPF and EIGRP complete the same task, but they come to their final conclusion for the best path in slightly different ways. On one side, OSPF utilizes a preset cost and bandwidth to choose the best path. On the other, EIGRP uses delay to find which path is best. Other than that, they also differ in administrative distance. Administrative distance is a metric for when two routers are connected but use two different routing protocols. To fix this problem, every router is given a table matching ways a router can learn a route to a certain number. The lower the better. For example, a route learned through direct connection is given a 0. In this case, if OSPF and EIGRP meet, the router will choose the path learned by EIGRP rather than the OSPF path. That being said, these can be customized by a network administrator. Now that we've gotten that out of the way, we can now continue on to learning on how OSPF actually works in a network. To allow for routers to actually communicate and build an OSPF network, they must first be able to communicate. This is done through OSPF hello messages. This is the primary way the router talks back and forth with each router. Once OSPF is activated, the router will first send out an OSPF hello message on all interfaces using OSPF. If connected to a router also using OSPF, that second router will respond. Once this is completed, The first router will then flood the network with a special packet called a link state advertisement. The link state advertisement holds within it information about the router that flooded it to the network. This can be information such as its IP address, subnet mask, and other information used to allow for a connection. These packets allow for every other router to learn each other. To keep them stored, each router has a link state database which can be sent out onto the network as well. Once completed, more hello messages will be sent out periodically to make sure that every other router is still up. If they are not, the cycle will begin again, and the router will flood the network with its LSA again until another connection is formed. The way OSPF works, after hellos are sent and LSAs have been stored in databases, there are two ways things can continue. In the case there are only two routers connected to each other, the routers will stay in this state periodically sending each other hello messages. Unless something goes wrong in either of the routers, each will not change their state or try to reconfigure the route. This state is called a point-to-point setup. Though good to know, you won't find this kind of setup unless you're in a very small network. The real interesting stuff happens when there are 3 or more routers on the network. In this case, after LSAs have been flooded, each router will begin sending election hello messages. These packets hold in them a priority value, which are automatically set and can be configured on the router. Each router will compare its own value with any other sent to it. If it finds a router with a high priority value, the router will switch to advertising that router instead. This will continue until every router advertises the same router's priority value. Once done, the elected router will be made into the designated router. This router will be the central point for information. Every other router using it to get their LSDB instead of using the LSAs sent out by other routers. As well, after this is completed, another election will ensue. Similarly, but instead electing a backup DR. After this is completed, the network will stay in this state unless the DR fails. When this happens, another election for the BDR will occur. The previous BDR replacing the DR that went down. To finish out, OSPF has an important setting for the setup of the network. Because of how the election works, sometimes this can be bad for a network. Especially in extremely large networks, having these elections for if a router goes down can slow down the entire network because of the flood of election hello messages. As well, having only one designated router for a large amount of routers requiring the designated router's database can overwork the designated router. As well, within the setup of the network, if there are a large amount of routers, this flood of LSA messages can slow down the setup. In these cases where too many routers can become a problem, there's a setting for OSPF that can help manage it. During the setup OSPF, the network administrator can configure the interfaces to be in different areas from one another. This allows for less congestion within the network since each area has its own designated router. As well, since it can be different on each interface, there can be routers set up as border routers. Though simple, this can add another degree of design to the network. These areas can help define different parts of the network, such as the backbone routers being separate from routers connected to subnets. Thank you for watching. This has been my presentation on OSPF as a concept by me, Jamie Maddox. Thank you.